Well, good afternoon to all of you. Please don't forget to turn in the homework that's due today. There's a big pile growing. I will post the solutions as usual outside my office. I do have a few homework sets from a week or more ago. Let's see, you, Gabrielle. So I've got some old work for a few of you. Let me also just remind you that your midterm exam is coming up on Monday, and it will cover all the material through the homework that you're turning in today, through last week's homework. So make sure you're prepared. As I've already mentioned, it's going to be a closed book, closed notes exam, but I will give you a copy of the property table handout, so you'll have all of that. It'll include the conversion factors. It'll include the inside back cover of the book, which includes, again, the conversion factors, gas constant data, that kind of stuff. So all that information is going to be available to you, but the equations, the methods of solution are something that you're going to have to know how to do yourself, to memorize, if you will. So please make sure you're prepared. I can't tell you how many problems are going to be on the test, but I will set aside time on Friday just for kind of general questions and answers and to give you a little more information about the exam. So I'll probably set aside like the last 10 minutes on Friday to take care of that. So if you have questions about anything and I wasn't able to answer them during my office hours, you can certainly come to class on Friday and I should be able to answer things for you. I'm sorry, say that again?
Is there any way you can post that so we can see where the conversion factors are? So you don't have to go through like 5 months to do everything.
Oh, you mean on my handout?
Yeah.
Oh, it's on the back cover of the handout. Just like it's in the inside back cover of your book, it's on the back cover of the handout. So yeah, I mean, I've been using basically my handout for everything. It's just this thing, and right on the back is all that. So these are the last 2 pages. Is the inside back cover of the book. Oh, of course, you're not seeing it, are you? Okay. I'm seeing it. It's right here. But yeah, it'll be there. So, and there's actually a table of contents. So the table of contents shows everything in the right order. But again, that's not something you can see right now. We'll look at that later. All right. So one thing I do want to comment on before we continue. When you're solving problems involving the first law of thermodynamics, which is really what this course is all about, make sure you're using the right equation. I mean, the first law in its most general form tells you that heat transfer is equal to change in internal energy plus the work, right? I mean, I guess we could put little 1-2s down here. We recognize there's different types of work. It might be electrical work, might be boundary work, might be paddle wheel work or shaft work. Then you just have several work terms. I mean, like for instance, one of the homework problems, which was maybe number 40 or something like that, had different types of work. Just got to make sure you include them all. What I would caution you on, though, is, I've mentioned how some of your terms are going to be positive, some will be negative, right? Heat added is positive, work out or work done by the system is positive, heat out is negative, work in is negative. I mean, don't change the equation. I mean, if you know that you have heat that's being lost from the system, don't change the equation to a minus Q. It's Q. When you calculate your heat transfer, it will have a negative sign associated with it, and make sure that you include the negative sign within the equation, but don't just arbitrarily change the equation because you know something is going to have a negative sign. The equation is the equation. It's the first law. It doesn't change. The signs will be based upon the data. Like, for instance, if you're doing work and you have a boundary work and you know that the boundary work is, well, let's say we're taking an easy case. Let's say it's a constant pressure process, so the boundary work is pressure times a change in volume. If the volume is decreasing, that means work is being done to the system, so it's negative work. But that negative sign will show up in the equation, right? Pressure times V2 minus V1. If V2 is less than V1, then it's going to be a negative term, and it'll have a negative sign. Don't change the equation to a minus W. Leave it as W, and then let the data of the problem determine what the appropriate sign is going to be. And then, of course, you can check it. I mean, you can use your logic and say, oh, yeah, I know work done to the system is negative, and I got a negative sign. You're comfortable knowing that you did it right, at least that the sign is right. So that's an important thing to note, is don't ever adjust the first law. Keep it exactly the way it's shown. let the signs be whatever the signs are based upon the data of the problem. Another thing to note is that you still have some problems where you're interested in, like, let's say, per unit mass data. In other words, if I just divide this upper equation by the mass m on both sides, well, then you get heat transfer per unit mass, you get work per unit mass. This would be the specific internal energy, which is really just internal energy per unit mass, right? So look at the problem statement. If it says something like present your answers in BTUs per pound mass, like one of the homework problems did, then you should really be using this version of the equation, the one where everything is lowercase. Everything's on a per unit mass basis. It's just going to save you a lot of grief if you use the right equations up front. So those are just a couple of points that I wanted to make regarding just general first law problems. All right, so we're talking now, new stuff. We're talking now about specific heats, right? Specific heat at constant pressure, specific heat at constant volume. We've seen how the specific heats are just properties, they're intensive properties, and we could use them like any other property. I know I've mentioned this before, but just because the word constant pressure or constant volume is in the title of the specific heat doesn't mean it has anything to do with a constant pressure or constant volume process, right? They're properties. You use them for whatever process you want. They're just called at constant pressure or at constant volume because they're defined as partial derivatives which have to be taken at a constant pressure or at a constant volume. Now, we're going to use specific heats not just for ideal gases, but also for solids, new pen, and liquids. So let's start looking at solids and liquids now. Can you guys read that okay? The pen is kind of malfunctioning a little bit. Well, it looks like it's only malfunctioning in the middle of the page. Maybe there's some oil on it or something. Solids and liquids. Yes. All right. So we're going to use specific heats for solids and liquids as well. So what I want to do is I actually want to start with my equation for enthalpy. Let's recall that enthalpy, by its definition, is just internal energy plus pressure times volume. Now, I've actually written it in its specific form. So this is the specific enthalpy is equal to the specific internal energy plus pressure times specific volume. And then what I want to do is write this in a differential form. So I'll write dH equals du plus dPV. And now what I want to do is just expand this second term on the right-hand side. Keep in mind that if you're taking the derivative of the product, you have to use the product of two variables. You have to use a chain rule, right? So this is then going to be pressure times dV plus specific volume times dP. So that's how we do that differential. This is a U, by the way. Okay. And now we have to make some observations about solids and liquids. So for most solids and liquids, the specific volume, which remember is just the inverse of the density, is actually very small and does not change. So let's say and is quite constant over a wide range of properties. Okay. So we kind of know that, right? I mean, if you have, let's say, a big bar of iron, you can take the specific volume or density of that bar of iron. You can now stand on top of that bar of iron. You've just added, many pounds per square foot, and it's not like the iron's going to squish, right? It's not going to change its density at all. You can put a big car on top of that bar of iron, and it's still not going to change its shape or size, right? We know that the specific volume, or if you will, the density, is going to be relatively constant. And we also know that it's got a relatively small specific volume. Remember, density is the opposite of specific volume. Something like gases have very low densities. right? Like air has a density of about 1 kilogram per cubic meter, but solids and liquids have very high densities, usually around 1,000 or so kilograms per cubic meter. I mean, many orders of magnitude different than gases. So having a large density means it has a small specific volume, right? They're the inverse. So what does that imply with regard to the equation above? Well, if something is quite small, then we can just assume that this is pretty close to 0. In other words, specific volume is close to 0. It may not be exactly 0, but this is an approximation. And if it's quite constant over a wide range of properties, you'll see that this is also called incompressible. And anybody who's taken a fluids class knows that the fluids class you've taken deals with incompressible fluids, right? They don't change their density. So in other words, dV is also going to be approximately equal to 0. So therefore, what we find is that the change in enthalpy is essentially equal to the change in the internal energy. Now, with this in mind, let's get back to the specific heats. Okay. We know something based on observation about specific heats. So we observe, or maybe I should say by empirical analysis, but we observe is fine. We observe that, again, for solids and liquids, U and H are strong functions of temperature, but very weak functions of pressure and volume. Now, I should note that we made the same observation with regards to gases. But it turns out it's also applicable for solids and liquids. It turns out that they're strong functions of temperature, but weak functions of pressure and volume. So let's go back to our definitions. We know that Cp is defined as a partial of H with respect to T holding P constant. But if, like for gases, H is a strong function of T but not of P, then that means this is essentially equal to dH dt. That should be a capital T, sorry. dH dt. And therefore, dH is equal to Cp dt. Similarly, the specific heat at constant volume, which is defined as del U del T V, again, since U is a strong function of temperature but a very weak function of volume, then this is also approximately equal to just du dt. So just like the enthalpy equation above, we find that du is equal to Cv dt. Okay. Now what we can do is we could simply plug both of those into the general equation above. So plug in above. I'm going to plug these two just into that equation above. So therefore, dH, which equals du, is actually the same thing as saying Cp dt equals Cv dt. And the dt's will now cancel. And therefore, Cp is going to equal, and therefore, Cp is going to equal Cv. Okay. Now, since the two of them are equal, we don't need to give them separate names anymore. In fact, we have a special new name. For solids and liquids, this is simply called C, heat capacity. So the heat capacity is the specific heat at constant pressure. It is the specific heat at constant volume, but we simply call it the heat capacity. Okay. So with this in mind, now let's go back to our basic equations. We know that dH is equal to du, which is now equal to just the heat capacity times dt, right? And this just comes from directly above here. Okay, so we know that du and dh are the same. They're both equal to c dt. And therefore, if we were to want to find an enthalpy change or an internal energy change, we just integrate. So the enthalpy change is equal to the internal energy change, which is then equal to, well, the integral of c dt. Now, another thing that we would note, and again, this comes from observation, we'll note that c is fairly constant over a wide range of temperatures. Okay? And this applies, again, to essentially all solids and liquids. Oops, I forgot my 1 and my 2 on my integration. All right, so since this is fairly constant over a wide range of temperatures, we're going to do the same thing here that we really did for ideal gases. So therefore, the enthalpy change is equal to the internal energy change. And if c is fairly constant, it just simply comes out of the integral. And then this equals the heat capacity times the temperature change. And this is the equation we're going to then use as we analyze solids and liquids in the first law to find the enthalpy change or the internal energy change. So H2 minus H1 is the same as U2 minus U1. It's the heat capacity times the temperature change. Now, you will find that, you know, I said here that it's fairly constant, not exactly constant. What you typically want to do is you want to use the value of heat capacity that is most applicable for the problem at hand. So in this particular case, since we're looking at the heat capacity really as a function of temperature, then I would use the value of the heat capacity at the average temperature of the problem at hand. If you don't have average temperature data, then just use whatever data is given in your book, which should be room temperature data. So we'll note that you should use C at the average temperature of the problem, or at room temperature if this is the data, or maybe say if this is the only data available. Okay. And as it turns out, our data is somewhat limited. So what you want to do is go to table A3. And now, if I could have our producer put the computer up. OK, so here's table A3. OK, there we go. If we look at table A3, you'll notice that there's several parts. The first part, part A, is liquids. So you'll see all these different liquids. And you'll see that the very last column is the heat capacity. Now, I don't know why the author does this, but he doesn't use the word heat capacity. He calls it heat capacity in the text, and as you're reading it, you'll see heat capacity. He should have just put heat capacity here. I mean, I've already shown that specific heat at constant pressure equals that at constant volume, although I will say that he does just call it specific heat. So he doesn't say constant pressure, constant volume, specific heat. He really should have written heat capacity. But nonetheless, you can see that for some liquids, like ammonia, you're given heat capacity data over a decent range of temperatures, although note that it doesn't really change by that much over the full range of temperatures. For other liquids, it just gives you one value. And somewhere in one of the notes, I guess this is at the bottom of the page, it says something about how if only one data is given, then it's at room temperature. But nonetheless, this is where you're going to go for liquid data. So A3 part A is data for liquids. If you, well, let's look at water because it's very common. You can see that between 0 and 100 Celsius, it changes from 4.22. It actually drops to 4.18. It drops by a whopping less than 1%, and then it goes back up to 4.22. So, you know, most problems involving liquid water are certainly going to take place at less than 100 degrees Celsius, because beyond that, the water is going to boil and it's not a liquid anymore. So clearly, water is a good illustration of how constant the value of the heat capacity can be. A3 Part B is data for various solids. In fact, it gives you some data for some liquids, some solids, even some foods is on here somewhere, but mostly this is solids. So these are solids. Really, A2A is liquids. B here is solids. And it gives you all sorts of solids, various metals, you know, things like glass and ice and other things. And then at the bottom is Part C, and here's your data for foods. We're not going to use the data for foods. You know, sometimes you see a problem that might involve an egg or a slice of butter or something like that. But, you know, it's just a pure substance like any other, and you'll just use the heat capacity data as appropriate. So anyway, this is where you're going to get your data from table A3. What I would like to do as an illustration then of how we use this is to solve another example problem. And I will note that this example problem is, gosh, this comes from the second edition. Yeah, this book's been around a long time. This comes from the second edition of your textbook. And it's the only one I'm using from such an old edition. But here's this problem. There we go. All right, so this type of problem is what we call a quenching problem. This is a very common type of problem. I'm not sure how many of you have had any kind of a mechanics or materials class yet, but you should all be aware that when you work metal, you can give that metal a whole bunch of different physical properties, mechanical properties, depending upon the way you work the metal. So for instance, if you have iron and you heat it up until it's a really high temperature, almost liquid or high temperature solid, is glowing bright orange, and you drop it into water, that iron is going to cool at a particular rate. If you drop it into some sort of an oil, it's going to cool at a different rate. If you let the thing just sit there in the atmosphere, it's going to cool at another rate. And depending upon how you work this iron, you can roll the iron, you can roll it when it's cold, you can roll it when it's hot, basically applying pressure. But all these are going to give you different physical properties for that material. So this is a quenching problem. In this particular problem, we have a certain mass of iron. It's at 90 degrees Celsius, and it's dropped into an insulated tank that contains 80 liters of water at 20 degrees Celsius. So what's going to happen is that the iron's going to cool and the water's going to heat up. It says that a paddle wheel driven by a 200-watt motor is activated to stir the water, which is also common. You improve heat transfer by creating some motion. This is called convective heat transfer. You'll learn about that in your 415 class. But nonetheless, this paddle wheel starts the water moving, and it says that it's activated for 25 minutes. And then finally, you reach equilibrium at 27 degrees Celsius. So at that point, the final temperature of the iron and the final temperature of the water are both the same at 25 degrees C. And you're trying to estimate the mass of the iron. Also, the paddle wheel might have some energy stored in it. Let's just ignore that. We'll assume that we have a system that's just water and iron. So that is our example problem. So let's set up the example. By the way, if it wasn't clear, I guess I didn't specifically say it, the reason we have these equations to find the internal energy or enthalpy change is so we can solve the first law, right? I mean, I get to the point where I just assume that that's obvious. Maybe it's not obvious yet, but we need either enthalpy or internal energy data to solve the first law for closed systems. That's why we use heat capacity for solids and liquids, so we can use this equation to find that internal energy or enthalpy change for the process at hand. So this falls right into that type of problem. All right, so here's our example. Now, it tells us that it's insulated. So that means that there's no heat transfer. Now, you may say, well, wait a minute. There has to be heat transfer. The water's picking up heat from the iron's losing heat to the water. But the iron and the water are both inside the system. You know, the amount of heat lost by one is immediately gained by the other. It's a net washout. When we talk about heat transfer or work, we have to identify the boundary of the system, and it's that entire container that's the boundary. There is no heat transfer across the boundary. That's the only heat transfer we deal with in a problem like this. We are never concerned with internal heat transfer. So Q is clearly 0, and I'll put Q12. We have our iron. So I'll just put Fe, since that's the chemical symbol for iron, and H2O for water. And the mass of the iron is the unknown. It's the first thing they tell us. The initial temperature for the iron is 90 Celsius. The water has an initial volume. So V1 of the water is 80 liters, and T1 for the water is 20 degrees Celsius. We know that there's a paddle wheel. So that paddle wheel has a 200-watt motor. So W dot, remember W is work, the rate of doing work is W dot. So W dot for the paddle wheel, I'll put PW, is 200 watts. And it's work or power that's coming into the system, right? So it's clearly a negative number. I didn't leave enough room for my negative, so let's just scratch that out, minus 200 watts. And then we would know that the work associated with the paddle wheel is just going to be the power, which is going to be what, kilojoules per second times time. Okay, so this is going to be minus 200 watts, which is the same as a joule per second per watt, and then times the time, which is 25 minutes. So 25 minutes, and then we have to multiply this by 60 seconds per minute for the units to work out properly. And then we also have to divide by 1,000, don't we? Didn't leave a whole lot of space here. Sorry about that. I guess I can write on the side. So we divide by 1,000 because there's, let's see, we got to convert joules to kilojoules. So there's 1 kilojoule for every 1,000 joules. So the units should all work out properly. Joules cancels, watts cancels, seconds cancels, minutes cancels. The only thing we're left with is kilojoules, which are the appropriate units. And the mathematic tells us that this is then minus 300 kilojoules. All right, so this is the paddle wheel work associated with this problem. And now let's just proceed with the problem. Okay. Are there any questions before I proceed? All right, so the first law, we know this is a first law problem. So we know that the first law tells us that the heat transfer equals the change in internal energy plus the work. Now, I guess I should be consistent, right? We know we have kinetic and potential energy, at least as a possibility, but we also know that for all these problems, it's negligible, just like this problem. Now, you might argue, well, there's motion associated with the water, so shouldn't we really include some kinetic energy? But the fact is that it's not really motion. I mean, it's not moving. You turn the thing on, and then you turn it off, it's not moving again, right? So yeah, there might be motion in the middle of this whole problem, but at the first state, the beginning, and at the final state, the end, there's no motion, so we can just assume it's 0. Plus, they didn't give us any information. Even if we wanted to try to find the magnitude of the kinetic energy change, we wouldn't have any way to do it. We don't have any velocity information, right? So we just assume that that's equal to 0. All right? And then, yes?
Wouldn't we already account for the work done by the paddle in W1, 2? Isn't that pretty much the contribution of the paddle that does to the entire system? So
Well, yes, but I'm not quite there yet.
Oh, okay.
So yeah. So, well, let's just do it now. We know that the work can be of any type, right? So there's the possibility of boundary work, although certainly this is a constant volume problem, right? So there's no boundary work. But then there's also the paddle wheel work. Okay. We might say boundary work plus other work, and then the other work in this case is a paddle wheel work. You had a homework problem where there was a paddle wheel work and electrical work, right? So you would say paddle wheel work plus electrical work plus boundary work. There's boundary work too. That homework problem was a piston cylinder device with a volume change. So there were 3 different types of work. In this case, however, the boundary work is equal to 0, you know, since there's no change in volume. So therefore, our first law really just becomes, oh wait, there's no heat transfer either. Even easier. We already stated that. So 0 is equal to the change in internal energy. And that's all that's left, oops, plus the paddle wheel. And that's all that's left of our first law of thermodynamics. Okay. Now, we have the final internal energy both of the iron and of the water. So why don't we say U2 iron plus U2 water. These are supposed to be U's. And then minus U1 iron plus U1 water. And then plus the paddle wheel work. And then we can actually combine the internal energy of the iron and the internal energy of the water plus the paddle wheel work. And then we would note that these are total internal energy change terms, so they're equal to the mass times the change in specific internal energy for the iron, and the mass times specific internal energy change for the water, plus the paddle wheel work. And last but not least, we're talking about solids and liquids. And since we're specifically talking about problems involving heat capacity, why don't we now replace the internal energy change by heat capacity times temperature change? All right, so we have mass times heat capacity times T2 minus T1 for the iron, and then plus mass heat capacity times temperature change for the water, and then plus the paddle wheel work. This all equals 0. This is the first law. This is what we're trying to solve for. All right. Now, what do we know? Well, we practically know everything, right? We don't know the mass of the iron. We know initial and final temperatures. We know that we have table A3, so we can find our heat capacities. We know the paddle wheel work already. About the only thing we don't know at this point is the mass of the water. But we have its volume, and we have its temperature. So can't we just go into our property tables? And we know that for liquid water, it's going to have the properties of the saturated liquid. Now, in all honesty, just think about this. At these temperatures, let's assume that this is taking place at atmospheric conditions, right? It's just a tank of water sitting there in the atmosphere. Any temperature less than 100 degrees Celsius is going to represent compressed liquid water. But we don't have good compressed liquid tables, although we do remember that compressed liquid water has the same properties as saturated liquid water at the same temperature. So as long as we know the temperature of that water, we should be able to find the saturated liquid conditions. And if we know the total volume, can't we just use the specific volume of the saturated liquid and divide the specific volume into the total volume, and that's going to give me the mass of the water? So we really do have the mass of the water. We just have to calculate it. So let's show that equation. So for the water, the mass is equal to the volume over specific volume. Why don't I just use the properties of state point 1? This is going to be the volume over VF at the initial temperature, which is 20 degrees Celsius. So yeah, we should be able to find the mass of the water just fine. So the only thing we don't know is the mass of the iron, and we're simply going to get that using the first law once we've found everything else. So now it's really just a matter of going through the mathematics. Now I do have to make one comment here as well. I made the statement, in fact I made it many times, that if you have water, then you always want to be using the tables, right? Table A4, A5, A6. And you could do that. I mean, you certainly could go into the property tables and just use, you know, UF at T2 and use UF at T1, and that would be a little more accurate. However, since this problem is trying to illustrate how to solve problems using heat capacity, I'm going to break my rule just this one time, and I'm going to use heat capacity data instead of using the data for compressed liquid water or saturated liquid water from table A4. Okay? But again, it's really just so I can make the proper illustration as I'm solving this particular problem. All right, so we get our data. And let's see, if we go into table A4 at 20 degrees C, we can look up VF. So I'm assuming you've all written the problem down at this point. That didn't work. Okay. So let's go get our data. All right, so we're dealing with water at this point. Saturated water. And this looks like the right table. You'll see that VF is 0.00100, what am I at, 20 degrees? 0.001002. So 0.001002 meters cubed per kilogram. So let us find the mass. So the mass, it tells us we have 80 liters of water, so we know there's 1,000 liters per cubic meter. So that means we have 0.08 cubic meters. And we divide that by 0.001002 cubic meters per kilogram. So we end up with a mass of 79.8 kilograms. Now this is the water mass, right? This is all for water. Let's get our heat capacity data now. So we're going to go into table A3A, and we're going to find data for water. We need the heat capacity. Keep running over my microphone cord. Oops, wrong way. Okay, so here's our data for water. Now, you can see that they give us data at 0, at 25, at 50. We're going to start at 20. And because we're dropping hot iron into it, we know the temperature is going to rise. We know that the data for about 25 degrees, actually all the way up to 50 degrees and even approaching 75 degrees, is going to be about 4.18. I mean, that's what's shown on this particular diagram. Sorry, this particular data table. So we'll just use 4.18 kilojoules per kilogram per Kelvin. So there's the heat capacity data. And then we'll go into A3 Part B for iron to get the heat capacity data. So let's see, here's iron. They only give us one number, so we really have no choice but to just use the value of 0.45 for iron. It doesn't tell us what temperature, but you know, presumably if it changed in a significant way over a range of normal temperatures, they would have given us more data. Anyway, so this is 0.45 kilojoules per kilogram per Kelvin. And we're essentially done. Now it's just a matter of going into our first law and finishing up the problem. Okay, so I don't want to have to rewrite the whole first law, so I like to use arrows. Hopefully that's pretty clear. So I'm just going to use that first law equation, and let's just plug in the numbers. All right, so we have 0 equals, the mass of the iron is my unknown, so 0.45 kilojoules per kilogram per Kelvin. And now we have our temperature difference, so the final temperature. And here's another thing that is worthy of a little discussion. I really should be using the absolute temperature scale. I mean, after all, my units are per degree Kelvin, right? However, I'm finding a temperature difference in this problem. I'm not using an actual temperature. I'm using a temperature difference to solve this problem. So isn't the temperature difference in Celsius the same as the temperature difference in Kelvin? I mean, if you want to, you can take T2 and add 273.15 to it. You can subtract from that T1 in Celsius plus 273.15 degrees. And the 273s cancel anyway, and you end up with a temperature difference in Celsius. So whether you simply understand that temperature difference is the same in Celsius and Kelvin, or whether you just add on that 273.15 and then just cancel it out on either side of the minus sign, it's entirely up to you. But to save time, I'm just going to use the temperature in Celsius and know that it's going to give you the same result as if I used that temperature difference in Kelvin. So T2 is 27, T1 is 90. That's the temperature difference in Kelvin, even though these are both degrees Celsius. That's OK. I didn't do this by accident. This is on purpose. OK, now we add to this the mass of the water, which we found as 79.8 kilograms. The heat capacity is 4.18 kilojoules per kilogram per Kelvin. And I'm going to do the same thing for the temperature difference here that I just did for the iron. The final temperature is 27. The initial temperature is 20. Even though those are both degrees Celsius, it's the same as the temperature difference in Kelvin. And then last but not least, I'm going to add the paddle wheel work. And the paddle wheel work is minus 300 kilojoules. If you look at all the units, kelvins cancel, kilograms cancel. We end up with all the right units, kilojoules throughout. And we just solve for our one and only unknown. And we get that the mass of the iron is 71.8. So 71.8 kilograms. And there's an example problem. Again, this is a quenching problem, but it's a good example of how one uses heat capacity for solids or liquids to solve these types of problems. Any questions on that? Good. Let me just leave this up here for a minute, and we will move on. Again, any questions? All right. Believe it or not, we're done now with Chapter 4. Okay, we've finished looking at the theory and all the example problems I'm going to look at regarding closed systems. And now we're going to start dealing with the open systems, which are also called control volumes. So we're making a fundamental change now in the types of problems. The types of problems that involve closed systems, or maybe I should say the types of problems that utilize our closed system analysis, are constant mass problems typical of sealed containers, right? Piston cylinder devices, rigid vessels, balloons, bags, anything that is sealed would be a closed system problem. But now we're dealing, or will be dealing, with open system problems. And these are problems that involve flow. So now we're going to start looking at those various devices that are used all over this real world of ours that do involve flow. Pumps, compressors, turbines, nozzles, diffusers, valves, heat exchangers. These are all flow systems, and we can't use closed system analysis for them because we don't have a closed system. I mean, we have flow through them. We have some mass coming in, we've got some mass going out. There's definitely changes within the system, and including mass changes because we have mass flowing through the system. So we now are going to begin looking at analysis of open systems. So let's just call this mass and energy analysis of open systems, control volumes. So again, a control volume is just another name for open systems. Right. Now, we did not have any kind of mass analysis for the closed systems, right? What's the point? It's a constant mass. So whatever mass we have is the mass we have. There's our mass analysis. But now things are different. Now we have mass flowing in. We have the possibility of mass either accumulating or diminishing within our control volume. Like, let's say you're talking about discharging a fire extinguisher. You start with an initial mass, you end with less mass. So there is a mass change within that control volume. There was no mass change in closed systems. Now there are mass changes. So the first thing we're going to actually talk about is the conservation of mass equation. How do we consider, how do we properly analyze mass in these flowing systems? So conservation of mass is the first thing that we cover. And after we're done talking about conservation of mass, then we'll talk about our first law analysis, which again, first law is conservation of energy, right? All right, so the first thing I want to do is just have you note a couple things. We're going to use the dot notation. You've all seen this, at least I hope you've all seen this in your calculus class. If you see a dot over something, that's just shorthand for time derivative, first time derivative, right? M dot is the amount of mass per unit time that's moving through the system. In fact, we have a name for this. It's called the mass flow rate. So we're just going to use m dot as the mass flow rate. We also sometimes look at volumetric flow rate. So v dot is simply the change in the volume with respect to time that's moving through the system. So this is called volumetric flow rate. And both of these are going to be used periodically as we solve problems. Another thing I want to note, for those of you who've had your fluids class, in fluids you use the letter Q for flow rate, right? But I can't use Q for flow rate. I'm using Q for heat transfer. So we don't use Q. It's actually better to use V dot anyway, because then it's obvious. V for volume, dot for time derivative of the volume. So the rate that volume moves through the system is the volumetric flow rate. So this is the Q from fluids, but we're not going to use Q. We'll just use V dot all the time. Let's note further that mass is equal to volume divided by specific volume. If we now take the time derivative of this, then we get m dot is equal to volumetric flow rate v dot over the specific volume. Okay. So these are just some of the relationships and terminology that we're going to need as we solve different types of problems. Okay. So with all this in mind, let's look at a pipe or a duct. I mean, a pipe is something that carries liquids. A duct is usually what we use to carry a vapor. But they're the same, right? Pipes are almost always circular in cross-section. Ducts are often rectangular in cross-sections, but it really doesn't matter. Let's just look at one. So there's my piece of pipe. And this pipe is going to have a flow area of A. So that's going to be the area. It's the cross-sectional area, if you will. And let's also note that in time dt, the fluid, which could be a liquid or a vapor, moves by a distance dx. So let's just say we're looking at this little increment of fluid that's right here. It's going to move by a small distance dx as it is about to flow into, or for that matter, about to flow out of the pipe, pipe or duct. Okay. And now, what I want to do is look at the mass of the fluid either entering or leaving. So the incremental mass entering or leaving is just dm. And that mass is going to have a certain volume, and it's going to have a certain density, right? So it's going to have some incremental volume, let's say dV, and it's going to have a certain density associated with it. I'll just use density now, but I'll modify this to specific volume later. So, right, volume has units of cubic meters, density is mass per cubic meter, so we just get mass, right? But we would note that the incremental volume is just this position change dx multiplied by the area. So this is actually equal to A dx times rho. Okay. And, or if we want to write this on a per unit time basis, we can just write this as dm dt is going to equal, and then here we would just have A dx rho dt. Or, if you will, isn't dx dt the change in position with respect to time? Isn't that just what we call the velocity? So we'll just write this as area times velocity times density. Or, of course, we know that density is just the inverse of specific volume, so we'll just write it as area times velocity divided by specific volume. Now, again, I want to remind you that we're going to use V's all over the place. Clearly, we're doing it a lot right here on this one page. That is velocity. It's a cursive letter V. At least it's supposed to be a cursive letter V. It has like little wings and tails on it. This here, the denominator, is lowercase letter v. That's the specific volume, right? It looks like the Greek letter nu more than anything and has a little point at the bottom. So don't confuse velocity with specific volume. So nonetheless, dm dt is equal to area times velocity over specific volume. Or to use the dot notation, we'll just say that m dot is going to equal velocity area over specific volume. Okay. Now, I will note that this equation applies at the inlet and at the exit of my pipe or my piece of equipment. If I have a pump, there's going to be a certain mass flowing in with its own characteristic velocity and area and thermodynamic state, specific volume, right? And it's going to have its own characteristic outlet conditions. You should not assume that the inlet and the exit conditions are going to be the same. They're definitely not going to be the same. Maybe sometimes, but most of the time, the pipe size is different going in and out. The velocity is going to be different in and out. The thermodynamic state is different. Therefore, the specific volume is different in and out. So we would actually like to rewrite this if we let I mean inlet and E mean exit, then we have the mass flow rate at the inlet is equal to the velocity times the area over specific volume at the inlet. And similarly, the mass flow rate at the exit is going to equal the velocity times the area over specific volume at the exit. So these two equations are going to be quite useful for us. Very useful. And of course, we'll eventually see where they're going to be useful and how they're going to be useful, but we'll get to that shortly. Well, actually, it'll be on Friday that we get to it. All right, now. Okay. All right. I'm sorry, say that again?
The specific volumes are...
No, no, no. I just put the subscript once, but I mean, it could have written this VI AI over VI, and over here VE AE over VE. But no, the subscript I and the subscript E each refer to all three of those terms within the brackets. So yeah, they're not the same. Now, maybe you asked this question because you've already had your fluid mechanics course. But remember, fluid mechanics deals with incompressible fluid flow. Every problem you'll see in your 311 class deals with incompressible fluid. Incompressible meaning that there is no change in the specific volume. So in an incompressible fluids class, like 311, V in and V out are always going to be the same. But this isn't a fluids class, okay? There will definitely be changes. I mean, if we have water going into a pump, and then we add work to that water in the pump, it's going to have an increase in energy. It's definitely going to have a different thermodynamic state going out as it does going in, right? So there's no reason to assume that since the state changes, that any of the properties are going to remain constant, that they're all going to change. So yeah, you never want to make that mistake in this class, unless you're told specifically that it's a incompressible fluids problem. Some are, most aren't. All right, so now let's do this. Let's consider the relationship between the mass change of our control volume and what's going in or out. So, let's say that we have a control volume, and just for illustration, I'll kind of give it that general shape of a pump. There's going to be some inlet pipe, so I'll just put I for inlet, and there's going to be some exit pipe. And this dashed line represents my control volume. I'll just put CV for control volume. CV is often the abbreviation that I'm going to use for control volume. So there's going to be some inlet and some outlet. And let's now just consider the relationship between the mass change of our control volume and the masses flowing in versus the masses flowing out. Now, it should be obvious, right? If we look at the mass in compared to the mass out, the difference between the mass in and the mass out had better equal the change in mass of the control volume, right? In fact, we can just write this as M2 minus M1 for the control volume. Okay. So basically, this tells us that the difference between what goes in and out equals the change in mass of the control volume, right? Or if you will, the difference between what goes in and out equals a change in mass of what remains. So, pardon me, this should be pretty clear. We will note that 1 equals initial and 2 equals final. Really, I should say initial state and final state in the control volume. Okay? So 1 and 2 are not the same as I and E. All right. We can also write this as a rate equation. Okay. So written as a rate equation, we would just say that the difference between the rate of the fluid that goes in less the rate that the fluid goes out would be the rate that the mass changes within the control volume, or if you will, just dm dt for the control volume. Okay. So both of these are going to be useful for different types of problems. Now, there's another thing I would note. Why do we have to assume that we only have a single inlet or a single exit? There are going to be many types of processes that have multiple inlets or exits. I mean, like, for instance, a heat exchanger. If you're transferring heat from, let's say, the hot combustion gases in your furnace to the air that you're heating up the house with, you've got air and combustion gas going in, and you've got air and combustion gas going out. You definitely have more than one inlet and exit. So for the case of multiple inlets or exits, we're going to use summations. So we can write, for instance, the sum of the mass of all inlets, summed over all inlet streams, minus the sum of the mass of all exit streams, well, there's only one control volume, right? So this is still just going to equal the change in mass of the control volume, or if you will, M2 minus M1 for the control volume. And if we want to use the rate equation, we would note that the sum over all inlets of the mass flow rate at the inlet minus the sum over all exits of the mass flow rate at each of those exits, well, this is just going to equal, well, still there's only one control volume, so this is still just going to equal the change in the control volume mass with respect to time. Okay. So, you know, I've derived this really primarily just based upon you having a logical understanding of what's happening when something flows in or flows out of a system. The difference between what goes in and what goes out equals the change within the control volume. Whether we write it in terms of masses or whether we write it in terms of flow rates, each of these is still an accurate equation. Now this last equation is kind of special, and we're going to use it a lot. This is called the continuity equation. Or we can call it simply conservation of mass. Okay. So this is an important equation that we're going to use for all sorts of different types of processes. Okay. And by the way, if we end up having a process where we only have a single inlet and outlet, then just get rid of the summation sign. If we have a problem that has multiple inlets and outlets, then include the summation sign. But ultimately, we're going to have multiple, or at least we're going to have the ability to solve problems that involve multiple inlets and exits. Now, there are special cases. And the first special case, oh, I shouldn't have gotten rid of that entirely. The first special case that we're going to deal with is called the steady flow case. Okay. So there's a lot of problems out there in the real world that involve steady flow processes. And in fact, the vast majority of the problems we're going to solve are steady flow processes. Now, what does it mean when it's a steady flow process? It's actually really simple. What it really tells me is that the mass in equals the mass out. That's all it means when we talk about a steady flow process. Aren't all these devices that I just mentioned steady flow processes? I mean, if you think about it this way, let's say we have a pump. If the mass is diminishing within that pump, at some point, isn't that pump just going to collapse upon itself? Well, then it wouldn't act as a pump anymore, would it? It would just be a junk piece. What about if you were accumulating mass within that pump? Well, pretty soon you have so much mass in there that it's just going to tear the pump apart, which means it's also not going to work as a pump. And the same thing goes with any of these devices, right? You're not going to be accumulating mass. You're not going to be diminishing the mass within these flow systems. It's going to remain constant. So if mass in equals mass out, well, therefore, we can say that the change in mass with respect to time for that control volume is going to equal 0. And hence, from our continuity equation, well, the sum over all inlets of m dot I is going to have to equal the sum over all exits of m dot E. All I've done is I've moved the m dot E term from the right-hand side of the equation, I'm sorry, from the left-hand side of the equation over to the right-hand side of the equation. So for steady flow processes, we would simply note that the rate that mass flows in over all the streams equals the rate that mass flows out. Now, another special case of this special case is what we call a single stream steady flow process. Now, if it's a single stream steady flow process, like a pump, like a compressor, like a turbine, like a valve, like a piece of pipe, there's only going to be one inlet and one exit. So for a single stream process, we would note that the summation simply goes away, and we simply have m dot I equals m dot E. Now, we can use the equations that I had presented above to simplify this, well, I shouldn't say simplify, but to modify this, remember mass flow rate is equal to velocity times area over specific volume. So the mass flow rate at the inlet is the velocity times area times specific volume at the inlet. At the exit, the velocity times area over specific volume at the exit is equal to the mass flow rate of the exit. So this is another really important equation. This applies to a single stream steady flow process. Now I might note that single stream steady flow is sometimes abbreviated SSSF. So you're going to see a lot of problems where you just see SSSF, and that's the author's abbreviation and will be my abbreviation for single stream steady flow process. So for any single stream steady flow process, we have this equation. Now, two last things to note here, then it looks like we're about out of time. Sometimes we replace the I with a 1 and E with a 2. Now, since we don't have to worry about the control volume anymore, we don't need to use 1 and 2 to represent initial and final state in the control volume. We're going to now begin to use 1 and 2 to represent the inlet and the exit state. So we could just as easily write this as velocity area over specific volume at the inlet. Oh, and then I go and I write an I again. 1 equals velocity area over specific volume at 2. Now, you don't have to do this, okay? If you are more comfortable, just leave it with an I and an E. But the book does this, okay? The author changes the I's to a 1 and the E's to a 2 for simplification. And then the other thing I wanted to mention, and then I know I'm out of time, if we have incompressible flow, in fact, I should really say for incompressible single stream steady flow processes, then this gets back to the question that one of your classmates asked earlier. Do the specific volumes remain constant? And the answer here is yes. If it's incompressible, then V1 is equal to V2, right? There is no change in the specific volume. So therefore, I simply get velocity times area at the inlet equals velocity times area at the exit. So this equation applies to an incompressible process for single stream steady flow. But most of the time, honestly, unless it specifically tells you that it's incompressible, then you're just going to use the basic equation for single stream steady flow, which is the equation that's given above. So it's this one up here that's typically used, okay, right there where the pen is. So that's all the time we have for today. Please don't forget to turn in the homework. Again, I've got some old work up here for, let's see, Miss Lou, Mr. Du, and Mr. Gabriel. So please don't forget to pick up your work. Don't forget to turn in the homework. I'll post the solutions when I get back to my office. See you guys Friday.